Hello everyone. In the last lecture, we discussed about the difference between the deformation mechanism in the quasi-static loading and under dynamic loading. Also, we have discussed about material strain rate sensitivity and the unique failure mechanisms that a material encounter under dynamic loading conditions. So now let us discuss about the applications for which we need the knowledge of dynamic behavior of materials. The application ranges from military to manufacturing industry, and it also includes seismic study, vehicle, aeroplane crash worthiness, and even rock blasting and oil well drilling. So we will talk about these applications one by one, if not all, at least few of them. So armor and anti-armor applications are in the military application, and then high strength lightweight impact resistant materials we generally would like to develop, which is a common goal in many of the applications. I mean that involves dynamic behavior of materials. Again, advanced computational methods for dynamic processes are to be developed for complicated materials model models that involve dynamic behavior of materials. Vehicle and aeroplane crashworthiness study are required for protection against accidental impact. Similarly, shielding of space shuttles or satellites from small meteorite impact. So these are the applications for which we need the knowledge of dynamic behavior of materials. Impact cratering is the depression of the surface of Earth or any other planet to hypervelocity impact of smaller bodies. So hypervelocity, this impact cratering produced by hypervelocity impact of smaller external bodies. Basically, these are the impressions made in the Earth's surface or other planet's surface. And then prediction of earthquake response also involved the study of dynamic wave propagation. And then planetary interiors, that is the dynamic processes inside planet, Earth or other planets, require these knowledges. And then we'll talk about the manufacturing industry, manufacturing processes a little later. And then the new non-destructive evaluation methods have to be developed for to study dynamic behavior of materials. Then hardening of metals, some of the metals or alloys can be hardened with the explosive loading. And then metal cutting with explosives, rock blasting, and oil well drilling. So let us discuss about the military applications, armor and anti-armor. Armor applications involve bulletproof vest or armor vehicles. Bulletproof vest we can call as a body armor. Armor vehicles can be lightweight combat vehicles or heavy tanks or even general vehicle for or VIP, very important persons, or any top government officials. So these applications need high strength impact resistance material. And about the anti-armor applications, a very common one is the shaped charge, which can have velocity up to 10 kilometer per second. We'll discuss about this in a while. And then kinetic energy penetrator, then explosively forced projectile, which is also same as shaped charge, and then plastic explosive head. So let us discuss the shaped charge, which is one of the most common anti-armor application. So basically this is the missile we have with this is shaped charge. So basically we have a target here, this is the target, and we have a metal cone, which is the main part of this shaped charge. So we should have a detonator here, and then we have high explosive. So this is the detonator, and we have high explosive. This is the metal cone, detonator, metal cone, and we have a sensor here. So basically okay, this sensor will be connected, the sensor will be connected to the detonator. So when this missile will hit the target, so the sensor will send signals to the detonator, and the detonator will explode. I mean, that means explode the explosives in there, and then this metal cone will take a shape something like this. So it will take a shape like this, it will transform to a long rod, and then it will ultimately hit the target. It will hit the target, and finally this is the explosion, the detonation, and the finally this will take a shape like this, and it will penetrate the target, and then finally we will the target will be defeated. Target will be defeated by the shaped charge. So this is what how the shaped charge work. And then again, coming to the kinetic energy penetrator, which is has an velocity like 1.5 to 2 kilometer per second. It's a long cylindrical rod made of heavy metals, made of heavy material, especially commonly used as tungsten or uranium. Then explosively forced projectile, which is same as shaped charge, we have already discussed it, but the main difference is disc is used instead of a cone in place of metal cone. So we use a metal disc. So that's the main difference. And plastic explosive head, this is another one. Plastic explosive head deforms upon impact, and then it detonates, and this detonation will produce shock wave, and the shock wave will reflect at the inner surface, of the armor, and then that will lead to fragmentation without any perforation. So this is done with help of a mechanism called phenomena called spalling. We'll discuss later about it. So basically the plastic explosive head deforms upon impact and detonates, and shock wave the propagates and reflect back from the inner surface of the armor, and that leads to fragmentation, and with the help of a phenomenon called spalling. So let us discuss about, for manufacturing industry applications, high speed fabrications, we will discuss about explosive welding and then explosive forming. So explosive welding is basically a solid state welding process where a base plate, which is let's say some carbon steel, can be joined with a cladding, let's say a thinner plate, something like this. This is the cladding thinner plate, and this is the base plate. Let's say this is made of carbon steel, and the other one is, let's say, some corrosion resistant materials, stainless steel or some other material. So we want to join these together. So what we do is we have a explosive layer on top of this material, and then it explodes here. It explodes here. So this is detonation. The explosives, here we have explosive. Basically the plates are joined together due to this explosion, and eventually it will also join. So basically this process can be used for metals with very different melting points. Some of these this type of joining is not possible through conventional welding processes. And also one advantage is that very large plates, that means large areas, can be joined together within a very short time. So that is one advantage. However, we need a great deal of knowledge about the explosive, how it explodes for this welding process. That is one requirement. And we'll talk about now explosive forming. So basically we have the workpiece. Here with the die with a die here. Let's say with this process you can make a board. So this is the board side view, let's say, and you have this workpiece. This is your workpiece. This is sheet, and you have your some clamp for this workpiece, and the entire setup is inside, let's say, earth surface. It is inside, so you have all inside. It's so this is okay, we'll give some more room here. So this is basically for vacuum, to produce vacuum here. So for reduce vacuum, this is the die, this is your workpiece. So we will have an explosive in here. This is explosive, and generally the explosive is not in direct contact with the workpiece, so we will have water in this. Water is a transferring medium for the shock waves. So shock wave will be generated. The water is the transfer medium, shock transfer medium. Shock transfer medium. So basically when it explodes, this explosives, when it explodes, this workpiece will take the shape of the die, So this is how the even some big boards are manufactured. So this is this will take a this shape. Now the flat workpiece will take a shape like this. So this is explosive forming, and then we will talk about another two processes: shock synthesis and shock consolidation. For shock synthesis is used for production of diamond from graphite. So we can have diamond from graphite. And for shock consolidation, generally used for powders, it can be metal powders, polymers, or ceramic powders, metals, polymers, or ceramic powders. To make any hard compact out of these powders. Basically the shock wave densifies the powder, to make some hard compact, and hard compact using through fracture and plastic deformation. And or fracture. Basically it happens like this. Suppose for example, if you were taking some powders in this tube, cylindrical container. So we have powder here, and then you have a concentric cylinder with concentric cylinder with explosive. So you have the powder here, and this is you have explosive. So when you you can detonate from here, detonator. So when it detonates from the top side, so the powder will transform to some solid from this side. So this way the commonly consolidated material is boron nitride and diamond for cutting tools applications. Okay. So similarly we can have the other applications. Basically hardening of metals is also important industry application. Shock waves are used for head filled steel, which is a manganese based steel, also another application is rail hardening of rail frogs, is the rail joints can be done with this process. And the metal cutting with explosives, this is nothing but the shape charge. This is the shape charge. And then rock blasting uses tension and compression wave to fragment the rock. This oil well drilling also uses shaped charges, which is loaded down the hole, and that makes the perforation for oil recovery. I beg your pardon. This is perforation for oil recovery. So let us discuss now about the structure of the course. What we discussed is the applications, and that is basically for to get the motivation why we need to study this course, dynamic behavioral materials. Now let us discuss about the structure of the course. In the introduction part, we talked about dynamic deformation mechanism and quasi-static deformation mechanisms, how they are different, and what is the difference in the failure mechanisms, what is material strain rate sensitivity. Now then we will talk about the stress waves, elastic waves, plastic waves, and shock waves. After that we can discuss about experimental techniques for dynamic deformation. There are intermediate strain rate test, and there are a little bit higher strain rate test, which is a split Hopkinson pressure bar is the most commonly used standard test, and then expanding ring test, gun systems, and there may be few more we will discuss later. And then the physics of plastic deformation at high strain rate and under shock waves, which is different than the normal high strain rate processes. And then failure mechanism already we have discussed in the previous lecture about the shear band and dynamic fracture. So we'll discuss about the applications and deformation of non-metals, polymers, ceramics and composites as well. So for the stress waves, the elastic waves are associated with the elastic deformation. Then when the amplitude of the stress wave exceeds amplitude of stress wave exceeds the elastic limit for a ductile material, and then plastic waves are generated. Plastic waves has a lower velocity than the elastic wave. So velocity of plastic waves is lower than the velocity of elastic wave. And again for shock waves, when material is bound, that is no lateral flow of material is allowed, no lateral flow is allowed, plastic deformation front is different. So this will lead to very different plastic deformation front, which will be very narrow, thickness very low. It can be even smaller than a micrometer, and also this will lead to, the shock wave will lead to phase transformations in the material, and even some chemical changes, chemical reactions in the material. So we discussed about the stress waves, and then after that we will talk about the experimental techniques of the dynamic deformation. So let us see the different strain rate ranges for different test or experimental techniques for dynamic deformation. So as we discussed in the previous lecture, this the unit of strain rate is second to the power minus 1. So this is, we already talked about how we can calculate the strain rate. So in this case, if the strain rate is very slow for creep and stress relaxation test, which is can be 10 to the power minus 9 to minus to the power minus 5, and then comes the quasi-static test, and that is 10 to the power minus 5 to almost it is 1, or you can take very close to that. And then for dynamic, we have dynamic low, we have dynamic high, and even a very high speed, high velocity impacts. So basically for the first two categories, the inertia forces are not important. Inertia forces are neglected, and for rest inertia forces are important. Inertia forces are imaginary forces that you must have studied earlier, and we'll discuss those later as well. So they are that increases with acceleration. And these are imaginary forces. So we'll discuss those later. So basically for creep and stress relaxation test, so we have creep tester and conventional even testing machines. Then for quasi-static test, which is we generally very commonly use test for, we can use hydraulic or servo hydraulic or screwed even testing machines. Then for dynamic test, for low speed dynamic test, we can have high velocity hydraulic pneumatic machines or cam plastometer. And then for dynamic we have expanding ring, split Hopkinson pressure bar and Taylor anvil test. Then for very high velocity impacts, inclined plate impact, normal plate impact, exploding foil, pulse laser, and then some explosive test. But basically for our dynamic test, split Hopkinson pressure bar is very important for us. This is the standard technique to obtain some stress strain curves in the dynamic range. So we will discuss about that. So let us discuss little bit details about the split Hopkinson pressure bar test. It is also called as Kolsky bar. So Hopkinson is the person who developed this test, but then Kolsky modified a bit. So basically the setup of this test is it's a very long setup. It can be its length can be a few meters long, and we have a gas gun, compressed gas will be used to drive our projectile, or like we can call this a striker bar. We have this striker bar assembly. We have a striker inside it. This is, we call it a striker. This is our striker or striker bar, or we can call it projectile bar. So we have some actually rail on support, on top of which we have all these arrangements. So we can have these type of supports. Here we have some, we call this is a incident bar, and then we have the sample here, very small sample, and then again we have another long bar which is called transmitted bar. So this is your striker bar, this is your incident bar. The projectile will hit the incident bar. This is your specimen, which is very small. Mostly it is smaller than the bar diameter. The bar diameter can be the common bar diameter can be 1 centimeter or even 2 centimeter. So then sample size is very small, in the millimeter range. This is transmitted bar, and we will have some shock absorber arrangement here. Shock absorber. arrangement. So we will have some strain gauges here. Firstly, one strain gauge in the incident bar, and other strain gauge systems in specimen, and then another strain gauges. So these are strain gauges. There can be multiple strain gauges, by the way, in one bar. So these are strain gauges. So basically the striker bar will hit the incident bar, and then the specimen is mounted here in between the incident bar and the transmitted bar. So basically the stress wave will propagate through the incident bar and then to the specimen, and it will transmit to the transmitted bar. So details about these tests we will discuss later. With the help of this test, we can obtain uniaxial stress strain curve for dynamic material. So we can obtain these type of plots. So basically this is like our the dynamic version of the very common our test we perform with our universal testing machine. And this is what I showed you. It is for compression. It is a compression test, but tension as well as torsion is also possible with Speed-Hopkinson pressure bar. So these tension is little bit tension and torsion have little bit complicated setup. I mean the same setup can be modified to have tension and torsion test. After that we will talk about the physics of plastic deformation. That we already know that the plastic deformation is mostly dislocation, involves dislocation motion, and then other forms of plastic deformation mechanism may be twinning. So basically we need to review our basics understanding of dislocations and dislocation movement, how slip happens, how twinning happens. So dislocation, slip and twinning. And then at high strain rate we will discuss about material strain rate sensitivity that we already introduced in the previous lecture. Strain rate sensitivity. And then under shock waves, so we will discuss about mechanisms of defect generation. Mechanisms of defect generation. Mostly we'll talk about point defects, line defects, and then interfacial defects, and even phase transformations, So point defects, as you know, interstitials and interstitial and vacancies, line defects, dislocations, and interfacial defects involved twins and stacking faults. And then we will talk about phase transformation. So these are basically we are talking about deformation mechanisms under shock waves. So after that we will talk about failure mechanisms that we already discussed in the previous lecture, that shear bands. and dynamic fracture, that we have seen that the crack can branch in dynamic fracture, and crack propagation velocity has a limiting value, and that we already discussed, and we will discuss in details in the later part of this course. And then deformation of non-metals is different than the metals, that we everyone probably knows about it. And then polymers, ceramics and composites, so we will discuss a little bit of that, and then we will discuss details of applications. We will probably have 1 or 2 classes on details of applications. Already we discussed some part of it. So with that we end today's lecture. So we will continue in the next lecture. Thank you.